All right, let's dive right into this explainer. If you're building modern AI applications, you already know vectors are the foundational language. But efficiently storing and retrieving them, well, that requires a completely specialized architecture. Today, we're taking a deep dive into Milvus. This is a profoundly impressive cloud-native database that is quite literally engineered for incredible speed.
And the absolute crucial point here is the staggering scale we're talking about, over 1 billion embeddings. Milvus isn't just built to search a few thousand vectors in some local dev environment. It is engineered from the ground up to search over 1 billion embeddings and to do it in mere milliseconds. It's the stark difference between waiting for a traditional database to slowly scan tables and having a highly tuned engine that immediately knows exactly where your data lives.
So here's our game plan for today. We'll start with a quick welcome to Milvus, then explore the control center, check out ingestion and indexing, and walk through the query pipeline. After that, we'll look at scaling and resilience, and finally, wrap up with some absolute best practices for deployment.
All right, Section 1, welcome to Milvus. Let's start right at the client layer.
First up, your AI application generates an embedding. And the breadth of connection options here is honestly incredible. Whether your team prefers Python, Java, Go, Node.js, or just hitting a straight REST API, you're covered. It also integrates right out of the box with major popular frameworks like LangChain and LlamaIndex. So right from the jump, Milvus is speaking the language of your stack and seamlessly accepting requests into the system.
But those requests don't just wander in randomly. They hit the proxy first. Think of the proxy as the ultimate traffic cop. It takes all that incoming data and enforces total operational order. It handles your authentication, dynamically routes your requests, balances the load, and strictly validates everything before letting it pass any deeper into the database. By efficiently dispatching these concurrent requests, the proxy ensures that no single internal component ever gets overwhelmed.
Moving right along to Section 2, the control center, or the coordinator layer.
Instead of relying on one massive, monolithic master node, which we all know can become a serious bottleneck, Milvus divides its brain into specialized coordinators. Each one is an expert handling a specific operational domain. You've got the RootCoord managing metadata and partitions. The DataCoord handles segment allocation and flush operations. The QueryCoord takes care of query scheduling, while the IndexCoord manages the entire index lifecycle. And they do all of this while constantly synchronizing the cluster state with etcd. That ensures a flawless single source of truth for the whole distributed system.
Next up, Section 3, ingestion and indexing. Let's look at the data pipeline. It's really a beautifully sequential flow. The client sends the data, which hits our traffic cop, the proxy. From there, the DataCoord takes over and routes it straight down to the data nodes, where it accumulates in growing segments. Once a segment is full, it gets sealed and safely flushed to object storage, like Minio or S3. Throughout this whole ingestion process, metadata is updating in etcd, and the system relies on message streaming through Pulsar or Kafka. This completely decouples the storage from the initial compute. But here's the thing. Raw stored data isn't exactly fast to search. That is where Approximate Nearest Neighbor, or ANN indexes, come into play. The IndexCoord schedules specialized index nodes to construct these highly optimized structures. We're talking about robust algorithms here: HNSW, IVF-FLT, IVF-PQ, and DISCAN. These undergo rigorous training, quantization for compression, and persistence. Effectively, Milvus is creating the precise memory structures that make searching billions of vectors even possible.
Which brings us to Section 4, the query pipeline. Let's talk about search execution. When a query finally reaches the proxy, the QueryCoord steps in to select the exact right nodes for the job. Critically, the required data segments are loaded directly into memory for maximum speed. From there, scalar filters are applied to narrow things down, and the actual ANN search is executed against those ultra-fast indexes. Finally, because your data is distributed across the entire cluster, the best results from all those different segments are merged and re-ranked, giving you the ultimate top K results to hand right back to the client.
Now, Section 5, scaling and resilience. How do we achieve high availability?
Because Milvus is totally cloud-native, it relies heavily on its Kubernetes deployment. It's monitored closely by Prometheus metrics and Grafana dashboards, ensuring high availability through some seriously amazing mechanisms. As workloads spike, nodes simply autoscale. Shards are continuously redistributed, and replicas are perfectly balanced behind the scenes. And if a node happens to fail, no problem. The system uses write-ahead logs, bin logs, and continuous streaming with Pulsar or Kafka to recover instantly. It survives node failures and performs rolling upgrades without skipping a beat. We are talking true zero downtime here.
Finally, Section 6, Best Practices for Deployment.
First off, isolation is absolutely key. You really should architect your Kubernetes deployment with completely isolated node pools for your query nodes, data nodes, and index nodes. To avoid hardware bottlenecks, use fast SSDs or NVMe drives for your hot data, while keeping a dedicated object storage layer for the bulk of it. You'll need a high-availability etc and a robust message queue to keep the cluster's nervous system intact. And hey, if your specific workload supports it, definitely leverage GPU acceleration for an incredible boost in search performance.
Beyond just the hardware, you've got to purposefully tune your configuration. You should choose HNSW if your absolute top priority is low latency and lightning-fast response times. But if you're constrained by hardware and need strict memory efficiency, IVF_PQ is going to be your best bet. And if you're dealing with massive data sets that simply blow past your available RAM, Diskinan is the way to go. Oh, and you also want to make sure you're tuning segment sizes, adjusting your cache, and always batching your inserts.
Lastly, you need the right engine under the hood. Make sure you back these software configurations with genuinely robust compute hardware. For a serious production cluster, you're looking at deploying anywhere from 16 to 64 plus CPU cores per node, depending on your workload, paired with 64 to 512 gigabytes of RAM. And please don't forget the pipes. You need a massive 10 to 100 gigabit high-speed network to support the heavy lifting. That ensures massive vector data flows between your nodes instantly.
Zooming out to the full architecture, Milvus is really nothing short of a masterclass in distributed database design. It brings together a completely cloud-native, highly available ecosystem that entirely solves the problem of latency and horizontal scalability for modern AI. It's this beautifully orchestrated dance of independent ingestion pipelines, specialized indexing, and lightning-fast querying that makes billion-scale vector search an everyday reality. Now that you understand exactly how a vector travels through this incredible system, from a simple API call all the way down to distributed memory segments, and how the architecture scales to meet the most demanding workloads on the planet, well, the only question left for you is, what will you build with billion-scale search?